In this video series, we have been looking at 6 different methods of factoring. So I want to start by, first of all, reviewing what they are and ranking them in an order to follow. Okay. So first of all, let me just list them. The first method we learned was looking at common factors. And that would be the number one starting place every time. The next thing we looked at were perfect squares and differences of squares. I would put differences of squares in the second spot. Because it's the most obvious of the two. And then perfect squares would be the next most obvious thing, but that takes a little bit more insight to notice that. The fourth method we looked at is factoring C when A is 1. And for all of these, we're assuming that we have a quadratic expression in the form that ax squared plus, that we have ax squared plus bx plus c. The fifth method was factoring A and C and then doing guess and check. Works nicely in certain cases, but not in others. And then the final method that we used was the AC method. The nice thing about the AC method is that it always works, regardless of whether you do any of the methods above it or not. But it can be time consuming to do the AC method. So it's good to quickly look at the other methods initially, especially pulling out common factors, because it reduces the amount of work that you would have to do. So now let's start at the beginning and look at examples of each, and so we start to recognize when to use which method. So here we go. Let's start with common factors. A good example of this might be if I had something like 3x squared minus 18x plus 27. When you look at that, once we talk through this, you might be tempted to jump to the AC method or the factoring A and factoring C and guessing your way to the answer if there are only a couple of possible combinations. But if you had immediately recognized that all 3 coefficients, A, B, and C, are multiples of 3, life gets a lot easier. So if we realize that this is 3 times the quantity of x squared minus 6x plus 9, we are left with an expression in parentheses that is much easier to factor in a second round. So by factoring out the 3, we made it into a much easier problem, and factoring constants out is very easy to do. So let's move on to the second method again, the difference of squares. I could add difference of perfect squares, but we'll just call this the difference of squares. So this method is, once again, it's fairly clear when it might work. So a couple of examples might be x squared minus 9. 9 minus x squared, we haven't worked with too many where we wrote it in reverse order with the c term first, but you can have c plus bx plus ax squared. So that would be a reverse order of what we had before, and 16x squared minus 25. These are all perfect examples for the difference of squares. First of all, when you don't have a coefficient, remember it's 1. So these should stand out as good candidates because we know that 1 squared equals 1 for this one, and 3 squared is 9. Once again, this is 3 squared and the coefficient on the x squared term looks like a 1 squared, and then we have a 4 squared and a 5 squared. So we have a lot of perfect squares here. But notice another thing, in every single one of these, the b term is missing. There is no bx. So bx is missing, which means b equals 0. So anytime you see a quadratic where their middle term is missing, and then there is always a subtraction in these kind of problems because it's a difference of squares. So if b equals 0 and you have subtraction, quickly check to see if the a term and the c term are perfect squares. If they're both perfect squares, then you can quickly find the difference of squares. Method 3 would be if we, instead of had the difference of squares, we had a perfect square. So in other words, if the quadratic could be a perfect square. Let's look at a couple of candidates for that. One good candidate would be if I had x squared minus 6x plus 9. Note that that's what we had up here after we factored out the 3. Another example would be 4x squared plus 12x plus 9. So you would know it's not the difference of squares because there is a middle term, a bx term. So we need to evaluate in each case whether it could be a perfect square. So the first thing you look for are the coefficients of a and c. So a could be expressed as 1 squared in this first case, and b could be expressed as 3 squared. So we know that it's a possible candidate for it because the first and last terms are perfect squares. In the second case, 4 is 2 squared and 9 is 3 squared. So the first and last terms are candidates for perfect squares. Now the key though is what's true about the middle term. Okay, so the middle term, for it to be a perfect square, the b value must be twice the square root of the a value, the product of the a and c value. So in case 1, we have the square root of 1, technically the square root of 1 times 9, or you could simply take twice the square root of a times the square root of c. That would be another way of looking at this. So in the first case, the square root of a was 1, and the square root of b, of the c term, I'm sorry, is 3. And so twice that would equal 6. So that's exactly what the middle term is. It's a minus 6, but we will be able to figure out how to get the perfect square in that case. It would just have to be two binomials that are both subtraction, or a binomial squared with a minus sign in the middle to get the negative 6. In the second case, we have the a term, the square root of the a term is 2, and the square root of the b term is 3. And if we double that, we end up with 12, which is exactly what we have for the middle term. Since it's a positive 12 in the middle, we would have a binomial squared with a positive sign, or an addition in the middle of it. So those are the first 3 methods. So you want to quickly look for common factors. Always look for that first. And then for method 2 and 3, note whether you have perfect squares for your a and c terms. And obviously, if it's a difference, you'll have no b term and there will be subtraction. If it's a difference of squares, and if it's a perfect square, that's a little trickier. The middle term has to be twice the square root of the a and c coefficient. I'm sorry, twice the product of the square roots of the a and c coefficient. But you can figure that out relatively quickly. So you can eliminate those as possibilities in very little time. And then that gets us down to the trickier 3 methods. Okay, so method 4, switch colors here. Method 4 was factor c if a is 1. So 2 quick examples for that method would be x squared minus x minus 6. And if we, another possibility would be x squared minus 5x minus 6. Now note right away, if a equals 1, you won't be able to factor anything out, so that eliminates method 1. In both of these cases, the c value would be negative 6, and 6 is not a perfect square, so we can eliminate methods 2 and 3 immediately. So what we would look for in this case is we would factor the c. There's no, the coefficient for a equals 1, so it doesn't factor down. So we could factor the final term into a 1 and a 6, or a 2 times a 3. So same thing over here, 1 times 6, or 2 times 3. Now you'll notice for the 1 and 6, we could end up, let me step back for a second. We know in both of these cases, since I have a negative last term, that we must be working with two binomials where the one of them is a sum and the one is a difference. And we need to get the middle term to be negative. So we need to have we need to be taking the difference of factors. So right away, as soon as I see that we have a sum and a difference, we're looking at the difference of factors. So because we have a negative c term, the difference of factors is what matters. And if we look at this, we could get a plus or minus 5 out of 1 and 6. And if we take the difference of 2 and 3, we can get a plus or minus 1, depending on the order. And we can see that the plus or minus 5 corresponds to the middle term in the second expression, and plus or minus 1 corresponds to the middle term in the first expression. So by factoring c, and notice in this case 6 didn't have very many possibilities, looking at the factors of c, we could quickly arrive at the possibilities for factoring each of these cases. Let's move on to the next method. So the fifth method is very similar to the method we just used, except that a will be factorable and c will be factorable, because we might have, so we would factor a and factor c, but that's going to then require us to guess and check. We'll have several combinations that we could try, and we need to guess our way to the answer intelligently with some guidance. So let me write an example. If I had 2x squared minus 9x minus 5, this is a very good candidate for this method because 2 can only be factored into 2 and 1, and 5 can only be factored into 5 and 1 or 1 and 5. So note, both the a coefficient and the c coefficient are prime, so there's only one possible way to factor each, the prime number and 1, and so we end up with having to try combinations, really just two different combinations. So we would know that we have to have two binomials. Since the final term is negative, the final coefficient is negative 5, we would have to have a plus and minus in the two binomials. And that right away indicates that we will be looking for a difference to determine the middle term. But the first term, there's only one possible combination. We could have 2x and x to get 2x squared. So the first terms have to be 2x and x. They could be in reverse order. Okay, so we could end up having, so they're interchangeable. And then the last, the constant terms have to be 5 and 1, and they could be interchangeable. So there are really 4 different ways we could try things out. We could put 2x up front, try the 5 as its constant term and the 1 is the other constant. And then we could and see if that works. If not, we can flip the 5 and the 1. And then if neither of those work, we could put the switch the x and the 2x and start over again. So it ends up being a total of 4 guesses to find our way to the right answer. But since each guess is pretty quick, we could end up getting to the answer rather quickly. The final method was using the full-blown AC method. So in the previous case, we had a limited number of guesses to try. But if I had an example like 12x squared plus 25x plus 12, we would have to guess and check for a long time. 12 factors a lot of different ways. 1 and 12, 2 and 6, 3 and 4, and you have 2 12s. So the number of combinations of flipping things around to arrive at the correct answer would mean that the guessing could take a long time. Now we do know, in looking at this particular case, that when we do factor it into the 2 binomials, we have to have, because of the positive 12, we would either have to have plus plus or minus minus. And because it's plus 25, we're clearly adding things. So we know that this is a plus plus case. So in order to use the AC method, we would right away know that we are looking at the sum of possible factors. But then recall that the AC method requires us to take the coefficient for A, which is 12, times the coefficient of C, which is 12, which gets us all the way up to 144. Therefore, there are going to be a lot of possible factors, but we will be looking for 2 factors that sum to 25, and it turns out it works out nicely. So we could then use those factors to split the middle term. And then grouping the 4 terms in pairs would allow us to figure out how to factor it completely. Now, why is this not a good candidate for all of the previous methods? First of all, no common factor. You have a 12 and a 12, but 25 does not share the factors of 12. So you can eliminate that right away. 12 is not a perfect square, so you can eliminate the next 2 methods immediately. And then when you just look at the sheer number of factors of 12, looking at all of the combinations of for the A being 12 and C being 12, makes it pretty clear that it would be daunting to use guess and check for this method. So you want to use the AC method when you have a case like this.